Let's take a look at multiple regression. We see from our chow data, the spherical lenses have a lot of variability. The baseline doesn't completely predict what the 5-year axial length is. In the spherical group, aspherical group, we can see that if you know axial length at baseline, you have a pretty good guess at what the axial length is going to be at 5 years. Not so much with spherical lenses. If we come up to our residual scatter plot, these are the spherical lenses, you can see that we have now, what this graph is, it's the residual of the baseline on 5-year follow-up. And so what we have done is we have adjusted for the baseline axial length, which means that we have taken out all variability due to that axial length. We see that a lot of this variability of axial length at 5 years can be accounted for by the level that you are at baseline. So what we're going to do here is once you remove that baseline prediction, you have this scatter that's basically for the axial length baseline, there's no longer any hint of linear effect for baseline relationship and 5-year follow-up. Down here, notice the range is from almost -2 to +2. In the aspheric group, most of the points are less than 1 on both sides. There are these outliers up here that weren't fit too well by the baseline model. But this is a lot of variability. So what we want to do is we want to say, well, what's creating this variability? Let's account for some of this. And the way we're going to do that is by using multiple regression. So we have some baseline measures. And we're going to see, are any of those baseline measures we've collected, can they help us predict this variability that we're seeing in this residual? So let's go to Analyze, Regression, Linear. And we have axial length at 5 years. We're going to keep axial length at baseline because we want to still adjust for that baseline, and then we want to see what else is predicting it. And so what do we have? We have age, we have sphere, cylinder, I'm not going to do axis, KT horizontal, the vertical, the eccentricity, E value is eccentricity. We have pupil size, we have central corneal thickness. Let's add those. And so what we're going to do is we're going to check and see if any of those other variables can predict axial length at 5 years. There's one other thing that I forgot to do, so we're just going to say OK and pretty much ignore what comes out. We want to data, select, and we want to only look if lens type equals, I'm not sure which it is, 2. Let's see. Let's make that lens type equals 0. Okay. Now we're just going to look at the spherical. So now let's go back to our Analyze, Regression, Linear. It saved all our settings, and so we say OK. Let's see what we get. Well, our R squared is 83% of the variance, so we've counted for a lot of the variance, but a lot of that is from the baseline, but there's additional variance. our overall model is statistically significant. We're greater than 0, which you would expect if you had 83%, counted for 83% of the variance. All right. So what we have here is our model. Remember, we had a, or y equals a plus bx. The constant is the a, and the b slope is the is this coefficient here. Unstandardized b is the coefficient. Standardized coefficients are just standardized for the standard error. So you divide the coefficient by its standard error, you get this beta. You can also tell, this lets you know, kind of, since it's been standardized by the standard error, the greater this number, the more it contributes. Also, the t-value says, it kind of weights them. So you'll see a correlation between these two columns in terms of the bigger the number, the more the variable is accounting for variance. We come down here, we look, we see age is almost significant. Sphere doesn't appear to be, which makes some sense because we're looking at axial length. We've already accounted for axial length. We have cylinder, not horizontal but vertical, not eccentricity but pupil size, and maybe a little bit of central corneal thickness. So we can see by our t-tests the weights of various weights and the direction that that goes. So the if we look at horizontal, vertical, it's a negative. So the steeper you are, I think this is how this works, the steeper you are in KT vertical, the shorter your axial length. So flatter eye leads to longer eye growth. Eccentricity was not significant, and then there's pupil size. Okay, we have some residual statistics here, and so forth. So this is multiple regression. Now, there are some things that we need to point out. Notice, for example, I said sphere wasn't significant, but then we had axial length. There's this, and horizontal wasn't significant, but vertical was. Whenever you do a multiple regression, you should also correlate, do a correlation of your independent variables. So we included, I'm just going to put everything in so that it's just quicker. And we run that. Now let's just take a quick look at this. For example, let's go to KT horizontal and vertical. Look at this. Horizontal and vertical are correlated at 0.9. That is really a positive correlation. But in our regression, it looked like horizontal didn't make any difference at all. How can two variables be almost essentially the same thing in terms of correlation, but one of them be significant and the other not? And that brings us to the problem of multicollinearity. So there is that when we run this multiple regression equation and we look at each of these variables independently, we look at them after we've controlled for everything else. So axial length at points with a coefficient of 0.645 is this is the coefficient, not the correlation, but the coefficient is that, and the significance is this after we have controlled for everything else. just like we said we added baseline in here in order to control for the other variables. So for example, when we look at age, we have controlled for baseline, axial length, and all these other variables. Now, if horizontal and vertical are essentially the same thing, when you look at horizontal and you've controlled for everything else, then you've controlled for vertical, then horizontal isn't going to be significant. Now, it's a little surprising that they both weren't significant because they're so similar. But in this case, vertical is winning the battle. It's slightly better than horizontal in terms of axial length. But if we come back, and so let's test that. Let's go to our correlation table and let's look at vertical and axial length. It's minus 0.147, and KT horizontal is going to completely destroy my hypothesis. Oh no, it's 5-year. Oh, I don't have 5-year on here. Let's add 5-year. 5-year correlation. Axial length at 5 years. Okay, now let's look. KT horizontal is correlated minus 0.636, so that's a pretty good correlation. Vertical is still lower. Okay, well, you know what? We're not just controlling for baseline or for the other one. We're controlling for all these variables. Let's just, for the heck of it, put in regression, linear. Let's get rid of all of these guys. And then just do horizontal and vertical. See what we get. Okay, you can see here that if we just put these two in, horizontal is the clear winner. Vertical is the loser. Remember, up here, vertical was the winner and horizontal was the loser. Let's go into our regression and let's add in baseline axial length. Now, vertical is more of the winner than horizontal. So this brings us to a cautionary, this is a cautionary tale. Your effects of each of your variables is completely dependent on the model that you are testing. So this is an important point, one that you must always be aware of. And in this case, you can see it's horizontal or vertical. One or the other is a winner based on who else is in the equation. We could add, who else was up here that was significant? Let's see, there was pupil size. Let's stick pupil size in here. Analyze, regression, linear, pupil size. What have we got? Now vertical is out and horizontal is in. This is just nuts. It flip-flops between who can win based on how much variance you're letting yet to be discovered when you're looking at these things. So pupil size seems to be most related to vertical, so it's cutting it out. And let's look back at our correlation table of pupil size and vertical versus horizontal. So here we go. pupil size, minus 4.3, minus 5.19. So pupil size is a little bit more correlated with vertical than pupil size is with horizontal. So it's kicking out the effect of vertical. And pupil size is pretty correlated with axial length at 5 years. So when you do a multiple regression, the reason you do the correlation table first is to verify your regression equation coefficients. So while we see in our coefficients up here that horizontal isn't significant, we can look at our correlation table and see that in fact horizontal is very correlated to 5 years. So when you find that sort of situation in your analysis, then you know that you're dealing with multicollinearity. So this is a very important feature, and I want you to always remember to check for that. I think we'll let that go for now. That's it for today.